In this video, I'm going to look at titration or pH curves. So in my burette, I've got some 0.1 mole per decimeter cubed sodium hydroxide. That's obviously a strong alkali. And in the flask, I've got 0.1 mole per decimeter cubed hydrochloric acid, and that's obviously a strong acid. And what I'm going to do is I'm just going to use some universal indicator, and we're going to follow the pH as we add small amounts of the alkali to the acid. So you can see from the colour of the flask now, I've added a few drops of the universal indicator, and the colour is indicating that before we add any sodium hydroxide, we've got a pH of about 1. That's consistent with HCl being a strong acid. So what I'm going to do as I add each small amount of sodium hydroxide, I'm going to plot the pH against the volume of alkali added, and we're going to generate the curve. One thing I forgot to say was that I'm using 25 centimeters cubed of acid in that flask. 2 centimeters cubed of alkali has gone in. The colour looks pretty much the same. The pH will have increased a tiny amount, so you can see my second cross is virtually in line with the first one, slightly higher. 6 centimeters cubed of alkali in now, and you can see we're just tracking that same course, ever so slight increase in pH. Colour looks the same, but it would definitely be increasing slightly. We're at 22 now, and again the colour looks so similar to it did at the start. I'm sure if we put some indicator in the fresh acid, it would be redder than it is now. There's a slight orange tinge to it. The pH is definitely increasing. Right, I'm going to change tack slightly. I'm at 24 cm cubed. The indicator is still in the sort of acid range, and it's still fairly low as well. Okay, but what I'm going to do is I'm going to set the burette away at just dripping in, one drop at a time, and then what I'm going to do is swirl the beaker. Hopefully if I can get the drops to go in sort of one every couple of seconds, we'll be able to track the pH. So sorry, this is probably like watching paint dry at the moment, but I'm being very careful to just, there it is, so it's a bit fast, 2, 3, 4, 5, a little bit faster. Okay, another drop, and hopefully what you're going to see are the gradual colours as we go from a stronger acid. We should hopefully get the weaker acid colours. Each drop's probably about 0.1 of a cubic centimetre, coming up to 24.8. 24.9, 25. Oh, we're getting a change now. Yellow. Next drop's gone into green now. Gosh, I sound almost excited here. 25.2 coming in now. Has that gone blue? Yes, it has. So these last few drops are causing a big shift in pH here. And just let that continue to drip in. So what's happened here is, as we've gone from 24 say to 25, we definitely started to see the pH rising. So we remember we had sort of the orange colour after the sort of rose, sort of red colour, so pH is climbing up now. And remember, these are just one drop at a time here, so not even that much alkali is going in. The next drop will have raised the pH quite significantly again, so we've got this sort of yellow colour here. We definitely got a green, so that's sort of pH 7. So if I put that up there on the next drop, and the next drop took us into the blue area. That's where we are now. It's not really going to change now. And so the next drop after that has taken us up to this pH range here. Now unfortunately my whiteboard is, I've set it up so it's really narrow. Maybe it's a bit of a mistake there. But what's happening is I'm still just dropping in the alkali. We're at 25.6 now. And we're definitely in the sort of top end of the pH range here. I'm just quickly looking at my pH colours on the wall there, and I would say we're definitely into sort of pH 12 territory. And what's going to happen if I continue to add this alkali, I'll put quite a bit in a second, the pH is now going to sort of stabilise at this top end, and this curve that I'm drawing is going to just level out at this top end pH wise. So the burette's sitting at 50 now, so I've added a further 25 cm cubed on from this point here, and the colour pretty much constant, sort of blue colour, and so the pH is just has levelled out at this level here. I'll draw the full curve, sort of smaller scale in a moment so you can see the full shape, but that's basically just running parallel across there now. So you can see I've drawn another curve with a different scale so I can fit the whole thing onto the whiteboard, and we've got this initial section where the acid is in such large excess, the addition of 2 centimeters cubed at a time of sodium hydroxide isn't really changing the pH markedly. As the alkali is sort of gaining its quantity, it's changing the pH more markedly now in this section. So this is where we started to see the orange colour. So it was red all down here, and it starts going orange. And then when we add smaller amounts of alkali, it's having a more dramatic effect on the pH. You can tell that from the colour changes. So we've got the sort of orange colour here, yellow colour here, then we hit that magic drop when we went to green, and then the next drop took us to blue. So to go from here to here effectively was a couple of drops of alkali, and so we get this vertical section in the pH curve, and then it sort of tracks this level line once it reaches its maximum pH. So this is the classic shape for a strong acid, strong alkali titration curve. So you can see I've written that up the top there. We've got sodium hydroxide we're using as our strong alkali, hydrochloric acid as our strong acid, and obviously that's the chemical equation for the reaction that's taking place in the flask. I'll just explain the equivalence point here. That's the centre of this vertical section, and what's going on there is we've got the equivalent number of moles of each chemical required by the mole ratio in the equation. Now if you remember, I used 25 cm cubed of 0.1 mole per decimeter cubed hydrochloric acid, which therefore means I need to use 25 cm cubed of 0.1 moles per decimeter cubed sodium hydroxide. So that vertical line there would be at the 25 centimeters cubed level. So you can see these titration curves, this vertical section here is telling you when the reaction is complete. If you do a regular titration, you would use, say, an indicator like phenolphthalein, and you're after that drop of that one drop from your burette that changes the colour permanently of the indicator. So we actually, now we know about this shape, we actually don't need an indicator. We could just use the curve, and it's the vertical section is telling us the equivalence point when we've got the right number of moles of, in this case, alkali to react with the acid. You'll notice also that the pH at equivalence, so that's the centre of this vertical section, the pH at equivalence is 7. And the reason for that is if you look at your product, we've got sodium chloride, which is a neutral substance, and we've got water, which is also a neutral substance. So we've got a pH of 7 because these are both neutral.